speaker, Asun Jiménez, from Federal University of Rio de Janeiro. No, that's my design. From Fluminense Federal University. And she's going to talk on a classification of singularities, singularities of elliptic Monge-Ampère equation in dimension 2.
Well, I want to thank Elsie for the introduction and Professor Destinam for the kind invitation to participate in this Congress. Well, I'm going to talk about this paper, this work, with my advisors, José Antonio Galvez and Pablo Mira. And this work is related with a certain classification of isolated singularities that appear in a class of elliptic Monge-Ampère equations. And although we are in the session of geometry, you will see at the end that the approach that we use is very geometric, and that we are also able to give a geometric application of our results. Let me start with a brief introduction of this topic of isolated singularities of PDEs. Well, we all know that for many quasi-linear elliptic equations, isolated singularities are removable whenever the solution relies in a certain sublevel space. That is the case, for instance, for the well-known example of minimal graphs. We all know that a minimal graph satisfies this quasi-linear equation, and Ber's theorem asserts that every isolated singularity of this kind of solutions is in fact removable. And this theorem of removability of isolated singularities can be, in fact, generalized for a more general class of quasi-linear equations. There exists a result of Rosenberg and Leandro that says that isolated singularities of prescribed mean curvature Killing graphs are in fact removable. This could be a generalization, a good generalization of this Ber's theorem. And of course, there exists removability criteria in the case we are interested in. That is the case of Monge-Ampère equations. Well, let me recall what a Monge-Ampère equation is. It is a fully nonlinear PDE that has this kind of expression. This expression here will be called as pure or classical Monge-Ampère equation, determinant of the Hessian of a certain function equal to a positive function. The fact that we impose here that this function is positive will guarantee that the equation is elliptic. And well, in dimension 2, that will be the dimension we are going to work in, this equation in red, this classical Monge-Ampère equation, can be written in this simple way. I call it classical because it originally appeared when the problem of optimal transport were studied. When the cost function you want to minimize to transport a certain measure from a point to another point is the distance. If you want to minimize the distance or quadratic distance, something like that, this kind of pure Monge-Ampère equations appear. Well, the simplest examples we can consider of this Monge-Ampère equation could be the first one when we put here the constant function equal to 1, determinant of the Hessian equal to 1. We are going to call this equation Hessian 1 equation. And a well-known equation in geometry is this Monge-Ampère equation, where K will denote the curvature, the Gaussian curvature of a graph in R3, the prescribed Gaussian curvature equation. Well, dealing with this Hessian 1 equation, the importance of this equation is due to their widespread applications in geometry. For instance, we can relate it with flat surfaces in the hyperbolic space. Also, it has a close relation with improper affine spheres and Lagrangian surfaces. And it's well known the relation given by Calabi between this Hessian-1 equation and minimal surfaces in R3. Well, a classical result concerning solutions of this Hessian-1 equation is this result of Jorgens that says that any C2 solution of this Hessian-1 equation, which is globally defined in the whole plane, must be a quadratic polynomial. That is, the solutions are elliptic paraboloids. Using this result of Jorgens, we could give a beautiful, simple proof of the Bernstein theorem for minimal graphs in R3, because the relation that exists between the graph of the equation that gives a minimal graph and a solution of the Hessian-1 equation is that a certain second integral of the minimal graph is a solution of the Hessian-1 equation. So if the second integral is a quadratic polynomial, we can deduce that the graph must be a plane. Okay. Well, this introduction concerning the Hessian-1 equation, just recall here also very famous result of Liebman concerning the equation of prescribed, now constant Gaussian curvature that says that any complete surface of positive constant Gaussian curvature, we may suppose k equal to 1, must be a round sphere. Well, by now on, we have just mentioned regular solution, but we are interested in singular solutions of these Monge-Ampère equations. What about singular solutions? Well, going back to the Hessian-1 equation, we know also by Jorgens that the simplest solutions other than those quadratic polynomials that may appear when we study the Hessian-1 equation are those rotational samples with a puncture at the origin. Okay? And in the case of surfaces of constant curvature equal to 1, the simplest example we can consider are those rotational peak sphere with two symmetric singularities. Okay? So singularities of this Monge-Ampère equation, in fact, appear. Well, in general, what those kind of singularities have in common? What kind of singularities, what kind of solution are we going to study? We are going to say that a solution, which is of class C2 in a punctured disk, has an isolated singularity at the origin if it cannot be extended smoothly across the puncture. Okay? If it doesn't have a well-defined tangent at the singularity. Observe here that the ellipticity of this equation, the fact that the determinant of the Hessian is positive here, what it's saying more or less is that the second fundamental form of the graph of the solution is definite, is positive definite. So we will have a convex graph. So by the convexity of this graph of the solution, we can directly deduce some consequences. The first one is that the tangent of the solution at the singularity, although it is not well defined, it will be bounded by convexity. Okay? And so a direct consequence of this fact is that the solution will be, in fact, extended continuously until the puncture. Okay? We will have a solution which has a singularity at a certain puncture. It can be extended continuously, and it has not a well-defined tangent, but the tangent cone exists. The solution do not become vertical at this point. And another direct consequence is that this limit gradient that we can define, as it is a limit of convex Jordan curves, it will be a point if the singularity is removable. It can be also a segment line, or it will be a Jordan curve. Well, let me start putting here the results we are going to prove. Our main theorem, our main classification theorem is the following. It says that if we take an analytic positive function that may depend on the coordinates, on the solution, and also on the gradient of the solution, and we consider this Monge-Ampère equation, we have the following. Suppose that we have a point x, y, z naught in R3, And we consider M1 as the class of all the solutions of this Monge-Ampère equation that have an isolated singularity at this fixed point. Then this class M1 of singular solutions is in one-to-one correspondence with M2 times set 2, where M2 is the class of regular, real analytic, strictly convex Jordan curves in R2. What I'm saying is that we have removed the case of that the limit gradient is a point, because this case is trivial, the singularity is removable, and the case of a line segment. Okay? Here, the map that gives this correspondence is the map that attach to each solution its limit gradient. And let me just mention that this Z2 that appears here is just a technical issue in order to distinguish the two surfaces that may appear with the same tangent cone. If we have a tangent cone, we could have two solutions of the same Monge-Ampère equation asymptotic to this tangent cone. One of them would have the second derivative with respect to x positive, and the other one, which is the reflected one, could have the second derivative with respect to x negative. This is just a technical issue. Okay? And this classification theorem is in fact a consequence of two more general results. The first one is a study of the asymptotic behavior of the gradient at the singularity. It says the following: if we start with data with a function in the Monge-Ampère equation, which is not necessarily now analytic, just of order ck, then the limit gradient at the singularity is a regular, strictly convex Jordan curve with this regularity here. Okay? And we also have an assistant theorem for a more general Monge-Ampère equation. Suppose now that our Monge-Ampère equation is this one here, where A is a matrix, symmetric, that may depend on the coordinates, the solution, and the derivatives of the solution. Well, if this matrix A and the function bar phi are real analytic, any regular real analytic strictly convex Jordan curve is the limit gradient of a solution of this Monge-Ampère equation. And in fact, this solution that we can construct starting with this initial data is in fact unique when we suppose here that this matrix A is equal to 0, and we impose that we are fixing one of these two options. When we take, for instance, that the second derivative with respect to x is positive. Okay? Well, before starting to show you how to prove this kind of results, let me give a remark here. I think it's important to remark that the classification theorem is not valid when we work with the general Monge-Ampère equation. Our classification theorem that attached to each solution a strictly convex Jordan curve do not hold in the general case when we have a matrix not necessarily 0. Why? Because, for instance, we can consider this linear Weingarten surface, which is a normal translation of a surface of constant curvature equal to 1. This linear Weingarten surface satisfies a Monge-Ampère equation of this type here. And nevertheless, this surface becomes vertical at the singularity. The gradient of the solution in this case is not bounded. It's not a singular solutions of our type. Okay? So our result is not valid for this kind of surface. And another counterexample would be the following. We have solutions of this general Monge-Ampère equation whose limit gradient at the singularity is a convex Jordan curve, but this convex Jordan curve may have points with Gaussian, with geodesic curvature equal to 0. is convex, but not strictly convex. Okay? So, well, let me start then explaining how to study the asymptotic behavior of the limit gradient at the singularity in the case of the classical Monge-Ampère equation, of the pure Monge-Ampère equation, when we do not have here a matrix A. We only have the determinant of the Hessian equal to a positive function. Well, the first main tool that we are going to use is the following. Suppose that we have a solution Z of our Monge-Ampère equation for a data positive function which is of order ck. And we can construct this metric ds squared here, which is, if you look at it, is conformal to the second fundamental form of the graph of the solution. And it happens that because of the ellipticity of the equation, this metric is in fact is Riemannian. Okay, we have a Riemannian metric ds squared associated to the solution, which is conformal to the second fundamental form. Then there exists a result of Hind and Weierstrass that says that our disk, our puncture disk, where we have defined our solution our disk. Our puncture disk endowed with this metric d squared, if the singularity of the solution is non-removable, in fact, inherits a conformal structure which is conformally equivalent to an annulus. Okay? If the singularity is not removable, what we are saying is that the puncture will open into a circle. Okay? So, as we are going to deal with solutions that has a non-removable singularity, we are going to pass to work with conformal coordinates for this metric ds squared, which we are going to be defined in a certain strip or in an annulus. In order to clarify this, it's not working. Okay. Let me define this strip sigma r. This will be the strip where we are going to consider conformal coordinates for this metric ds squared. Or equivalently, we can work in this strip or in an annulus by a conformal diffeomorphism to pi periodic. We can identify this strip with this annulus. Here, the real line is going to be mapped in this unit circle. The real line or the unit circle equivalently, they correspond to the singularity we have at the origin. Okay? Well, what are we going to do then? We are going to parameterize the graph of our solution, which would be x, y, and z, the solution, in terms of these new parameters, u and v, which are defined in this annulus gamma. Okay? Observe that here the parameterization can be extended also until the boundary of the strip, until this red real line, collapsing all the real line into the puncture. Okay? We may suppose also up to a reparametrization of the equation that this puncture appears when x and y are 0, and that the height which that the solution attains is equal to 0 too. If not, we could make a translation and reparametrize the equation. Okay? What I'm saying is that I'm going to take parameters u and v in this strip, which are going to be 2 pi periodic, and I'm going to parameterize locally my surface, the graph of my solution, in terms of these new parameters. Well, our first result concerning the regularity of the limit gradient is the following lemma. It says the following: consider a data, a function in the Monge-Ampère equation of order ck. Then this vector function z with the coordinates, the solution, and the gradient will be a function of order ck alpha, not only in the strip but also at the boundary of the tree. Okay? How can we prove this result? Well, the first step would be to deduce that because of z is a solution of the Monge-Ampère equation, this vector function, big Z, satisfies this first order system with respect to the coordinates u and v in the strip. We can then derivate once more and deduce that the gradient of this, the Laplacian of this vector function z is a certain function h depending on z and their first derivatives. So we can apply a recursive bootstrapping method and some boundary regularity results, and we deduce the desired result. I'm not going to enter into details. And also, let me say that with the same effort, with the same techniques, if we start not with CK but with an analytic function, the resulting vector function will be also analytic till the boundary. Okay? But this is a regularity of x, y, z, p, and q as functions of u and v. We want to prove that the curve gamma p, which is p and q, the limit gradient at the singularity, is in fact a regular curve as a curve in R2. How can we prove the regularity of this limit gradient? Well, we want to prove that this parametrization of p and q along the points of v equal to 0, that is the points of the real line, is never equal to 0. We don't have points in the curve whose derivative vanished. Okay? Well, the way to prove this, I'm not entering in too much details, is the following. We are going to consider this new function as theta, which is just a rotation of the x-axis. We are taking the real line here, and we are making a rotation. We know that our parameter, we have a conformal diffeomorphism between this disk and a certain strip. Okay, u and v are here, and here we have coordinates x and y. Okay, and we know that this real line in red will be, in fact, crossed just by two nodal curves of this function s theta. These two nodal curves correspond to these two edges. We will have just two nodal curves of this. Nodal curves are curves where this function vanishes, crossing this real line. Okay? The second step of the proof could be to note that the Laplacian of this function is a function f that vanishes when x and its gradient vanishes. So we can apply Nodal theory to assert that we cannot have points where the curve gamma has tangent equal to 0, because those points, those singular points, correspond to crossing points of nodal curves of this function x theta. So if we had another point u naught where the gradient vanishes, we could have another nodal curve here, and this could be a contradiction with the first item I wrote here. Finally, varying this angle theta, we deduce that they cannot exist singular points for this limit gradient. Okay. Now we know this is a regular curve. We have a regular curve which is a convex Jordan curve, but we want to prove that this curve is in fact strictly convex. How can we prove that the geodesic curvature of this curve is not 0 anywhere? Well, the way to prove this is again using Nodal theory. Now observe that because of our graph is a convex surface, we can parameterize the second fundamental. We can use these parameters u and v, which remember are conformal for the second fundamental form, and write the second fundamental form of the graph in this way. Now, if we compute the Laplacian of this function here, rho, we deduce that the Laplacian has this expression here. And the normal derivative of the Laplacian across this real line is related with the geodesic curvature of the normal, of the limit normal, by this formula. So what do we have? If we had a point here, U0, where the geodesic curvature of the normal were 0, the normal derivative of this function rho could be 0 at this point. What are we saying? That we could have a nodal curve of this function rho crossing the real line at this point. But this is impossible because our graph is regular away from the puncture. So we cannot have points where the geodesic curvature of the limit gradient is equal to 0. Okay? This is the argument I was saying. If we had a point with geodesic curvature equal to 0, we could have a nodal curve crossing the real line, and this could be a contradiction with the regularity of the graph. Well, this could be the explanation, a brief explanation of the proof of the regularity of the limit gradient. Let me now say how can we prove an existing result in the case that we have a more general Monge-Ampère equation, when we have here a general symmetric matrix. The result could be the following. Suppose that we have now analytic, we need analyticity now, two data, a matrix and a function which is positive. And consider in opposition that of the procedure that we did in the theorem, now we are not going to start with a solution. Now we start with the limit gradient. Now we will start with a function, with a curve which is regular, negatively oriented, and strictly convex. This orientation is just a technical restriction that we are going to understand later. We are going to start with this function, and we are able to construct a solution of this Monge-Ampère equation on a certain puncture disk that has an isolated singularity at the origin, and whose limit gradient of this solution we have constructed has in fact this curve as limit gradient. Well, how can we prove that? We just start rewriting our equation in this way with coefficients A, B, C, and E. And we consider this first order differential system, which could be the associated to the other case, the other simple case that we saw at the beginning for the case when the matrix equals 0. Now we have this first order system with respect to the coordinates U and B. And we know that by the Cauchy-Kowalewski theorem, and because of all the data we have considered are analytic, we have uniqueness, we have existence and uniqueness of solutions of this first order system when we consider the initial data x, y, z, p, and q equal to 0, 0, 0. We are supposing that the puncture is centered at the origin, and we are taking as limit gradient the curve gamma, which I remember is a convex curve, which is in fact strictly convex, and we have chosen a certain orientation in it. We have oriented it in a negatively way, okay? Well, we consider this system and we find a solution which is unique. The next step could be the following. Consider the Jacobian of the chain of coordinates between the coordinates x and y, which are defined in the puncture disk, and the coordinates u and b defined in the strip, okay? The normal derivative of this Jacobian along the real line is related with this limit gradient in this way here. Since the curve we have chosen is negatively oriented and strictly convex, this quantity here is strictly positive. So we have that the normal derivative of the Jacobian along all the real line is positive. Applying inverse function theorem, we can assert that this Jacobian in a neighborhood of the real line in the upper half plane must be a positive function. What I'm saying is that we can do a chain of coordinates. we can express our z, which was one of the functions appearing in this differential system. We can express it in terms not of the coordinates u and v, but in terms of x and y. And because of the system that it satisfies, it's an easy computation to show that in fact z is a solution of our Monge-Ampère equation. Okay? Now we have a solution of the Monge-Ampère equation, which is a local graph. But we want to prove that this solution is well defined, that we have a real graph, we don't have a multigraph. The way to prove that our local graph is in fact a graph could be applying some classical theory of the Legendre transform of the graph. I'm not going to enter in details. Well, here finishes the existing theorem. The uniqueness theorems for the simplest case, for the case of pure Monge-Ampère equation, could be the following. Suppose that we have an analytic function and consider the pure Monge-Ampère equation. Suppose that you have a solution in a punctured disk with an isolated singularity. Then we have proved before that the limit gradient of the solution at the singularity must be a regular, strictly convex Jordan curve, which is in fact real analytic. Secondly, by the existing theorem I have just mentioned, we can recover our solution in terms of this limit gradient. We have a solution, we have a limit gradient, and we can recover our solution in terms of its limit gradient. And finally, if we have another solution, Z prime, with the same limit gradient, with the same curve as a limit gradient, and we impose that this solution, Z prime, also has second derivative positive, we are choosing one of the two options. These two solutions, Z and Z prime, must coincide, must agree in a certain neighborhood of the origin. We have, in fact, uniqueness of solution because of the uniqueness of solution given by the Cauchy-Kowalewski theorem. Okay? Well, summarizing all that I have said till the moment. Suppose that you have an analytic function which is positive, and you fix a certain point in R3, x naught, w naught, z naught. Consider M1 the class of all the solutions of this Monge-Ampère equation that has an isolated singularity at this point, x naught, y naught, and its height and this, at the puncture is z naught. Then the map that says that from each solution its limit gradient gives a one-to-one correspondence between this class M1 and M2 times Z2. I remember that M2 is the class of regular, real analytic, strictly convex Jordan curves in the plane. Okay? Well, from now on, I want that you see the geometric approach behind all the proofs of our results, but I want to finish the talk giving an explicit, I think a nice explicit very geometric application of this classification result. Well, suppose that you have an open disk and you have an embedding of this open disk in R3 with a puncture. Okay? We are saying that this embedding has an isolated singularity as this point of the disk, this point P naught, if this embedding cannot be extended smoothly across this point. Okay? And now consider in R3 a certain positive function K, like a density. You put a density in R3, and you'd want to find the surfaces sigma embedded in R3 that at each point of the surface, its Gaussian curvature, its extrinsic curvature, is equal to this density you fix it at the origin at this point. Okay? Well, applying our classification result, what we obtain is the following. The set of all the embedding analytic surfaces that solve this problem of prescribed curvature and that have an isolated singularity at this fixed point of R3 are in one-to-one correspondence with the class of regular real analytic strictly convex Jordan curves now in the sphere? Well, let me explain briefly the two things that maybe were here. The first thing is that this Z2 that appears before have disappeared. It's just because when we consider a surface, a convex surface in R3, we are fixing the orientation that makes the second fundamental form positive definite. So positive defined. So this ambiguity, these two possibilities disappear. We are choosing one orientation. So we only have in a position of having M2 times Z2, we only have M2. But we are not saying that those surfaces are in one-to-one correspondence with flat curves. We are relating them with the limit normal, with curves which are in S2. Why is this? Because if you have an embedding of finite area and a positive curvature in R3, you will know that this embedding, this surface, is in fact a graph in a certain direction that you don't know what it is. You know this is a graph. So you know that at the end you will have a solution of your Monge-Ampère equation of prescribed curvature, but you don't know what is the direction with respect to which your surface is a graph. You don't know what is the direction, what is the direction you are going to project your normal, your limit normal, in order to obtain this planar curve gamma we were working with. So we are working directly with the limit normal in the sphere. And let me say that the importance of this result is that this classification of isolated singularities of Monge-Ampère equation related with surfaces of prescribed curvature were only known in the case when the curvature is equal to 1. Now here we are not imposing that the curvature is positive. It could be a function depending not only on the coordinates in the base, but also on the three coordinates in R3, and also could depend on the tangent. It's a general function. And let me say in order to finish that we are working to obtain more general results, to generalize this result when the case we are not working with convex surfaces in R3, but we are working with convex surfaces in other more general ambients as workspaces and something like that. I think I'm going to finish here. Thank you very much.